do a limitation a couple times. Basically, we have a noise formula that generates some pretty good craters, but there's a problem. The Voronoi, like to do this, we are basically eating so much of the, like, here, let's take a look. Uh, we're right here. So let's find our last domain scale. So our last domain scale is a quarter, and that's of this like already pared down piece of Voronoi noise. And we end up with an issue with precision, which you can see right here. So from a distance, these look like pretty good craters. Um, but when you get up close to the surface, you get this really jagged texture that is not pretty and also non-functional for like our actual use case, which is walking around on this surface. So like if I drop in here and we fall down and we land on the rim of this crater and we start walking, you're gonna kind of see what I mean as we get close enough to cause these precision issues. So like here, where it's mostly the contribution of the noise that we use to like mask out the tops of the craters, it's fine. But when we get into the crater wall, that doesn't have that. I mean, it's still jagged, but it's not as bad. But when we get into the crater wall where it's less masked and more just the Voronoi noise that we're using, you'll notice that we like the precision issues get really bad. The wall is really jagged. It doesn't look good. Um, so let's just run down this wall for a bit. Um, so basically, this approach, while it does sort of work to generate the patterns we want, doesn't really work for our use case at the scales we're talking about because we end up with situations like this, where we're just stuck, we can't move. Okay, we got out. Nice. But you can see the problem. This is not really very nice terrain to like traverse. I'm trying to really get into some of the steeper parts of the wall. So we need a solution to that. We need a different option. Um, and sadly, I don't think we're going to be able to overcome this issue using solely the fast noise library because the precision issue is coming from the fast noise Voronoi implementation. So I was thinking about this last night, and I think what I want to do is in our planet noise, we're going to add a couple more virtual methods. Um, so we have this method that is required to be implemented, right? And we have this method that is implemented. So what we're going to do is we're going to add a couple flags. So we're going to add a boolean um, use pre-process false bool use post process equals false. We're going to add C amplitude scale frequency scale sea level min bound max bound. Okay, and we're expecting normalized points to be fed into this function. And so what we're going to want to add here, we don't want to have to implement these. So we're going to add virtual void pre-process vector position, and that's going to return an F vector, right? Um, and by default, we're just going to return the position. And we can actually have these on inline since they're just a single line. Post process, return position. And then we don't want to have to always be re-implementing this get noise from position, right? So what we actually want to do, if use preprocess, actually, let's do it like this. These will just deal in offsets, right, until the very end. So we'll do noise value, noise value equals 0, noise value equals preprocess position. No, no, no. That's not what we're going to want to do. Okay, I take it back. Because this needs to feed in to the next layer, we are going to do it with the edge point method. We're going to do pre value equals this, preprocess edge point. I guess it makes sense, sort of, to have the like full logic to recalculate the point in the preprocess. So that actually makes it easier because now we can just say edge point equals position. I'm also gonna change this to be consistent with our naming conventions. In position. Oh, fine. So first, we run the preprocess. If we have the flag for preprocess, we don't want to be running it if we don't have to. Then we run our noise formula on the preprocessed point. And we output that. Then we run a post process on it. and then finally we return the adjusted point. So this should be basically pretty lightweight here, like in most cases. We're not doing anything different than we were already doing, except for adding two Boolean checks, which are pretty efficient. But it gives us the option when we're building our initialized node to set these flags to true, and then to do a custom implementation of pre and post process. So I was hashing out the ideas on how to get a good crater noise with like high precision last night, as I was going to sleep, and I came up with some ideas. I think, um, and let's just draw that real quick to get them out of my head and onto paper. All right, file, new, don't save. So say we're on a sphere, right? And we're going to use Voronoi noise, which is like cellular noise, and we're going to do a 3D Voronoi noise, and it would look something like this, right? Where Voronoi noise is basically generating a bunch of distorted cells. That's why sometimes it's called cellular noise. And this is in 2D, but these would be in 3D space, right? There we go. So for each of these cells, there will be a centroid, which is like the shifted point after running the gradient that is effectively like the center of the node, right? And what we're going to do is for each given point on the surface of the sphere, we're going to figure out which cell it's in, where the centroid is at on that cell, and what the closest distance to the nearest cell wall is in three-dimensional space. And we can use that to then construct a circle. I mean, it's not a circle actually, it would be like a distance field, but effectively it's a circle, or it's actually effectively a sphere, right? Because it's a radius from a point in three-dimensional space. But for this, for the purposes of this, we'll say it's a circle. Then we can have a curve something like this. Hang on. Something. We can have a curve something like this. And we can plot our distance from, like, we can plot our normalized distance from wherever we're at. If we're within this radius, we can plot our normalized distance on this chart to determine our offset. And that should have the result of creating a side view that looks sort of like this. Oh, well, let's draw a little bit smaller. Which is exactly what we want for a crater. There's some other nice things about this. I was trying to figure out how I could do like ejecta, but with this, we could also cast like ejecta rays from that center point, potentially. So today we're going to work on that. And the first thing we got to do is make it, like, it's going to be easiest, I think, to prototype this in HLSL instead of C++, um, because we can get immediate visual feedback using HLSL in the material editor, whereas like we would have to get the whole thing completed to really see if it worked in C++. So we're going to build a HLSL prototype of this idea, and the first thing we have to do is what I was chatting with a coworker last night about, which is to build a Voronoi function that returns a float 4. The first three values are the XYZ position of the center of the node that is in the cell that the sampled point was in. And the last value is going to be the shortest distance to the nearest the shortest distance to a wall, right? Because we need this to form the radius that we can have without overlapping another crater. Because as soon as we have like a radius going like outside the walls, we can overlap, and we don't want that. We can manage our overlaps by having we can manage our overlaps with FBM, right? Like the fractal, when we add a fractal layer to this, that will manage overlaps by itself because we'll be generating smaller and smaller layers of noise with more craters. Um, so that's why we need this minimum value to the cell wall, and we can kind of just visually verify what I'm talking about here. Like if this is the smallest radius, and you can kind of see that as long as we're obeying the shortest distance to the nearest wall, we should never overlap craters. We can also randomize our radius here. Like it doesn't have to be the shortest distance, it could be shorter. And we'll have some kind of factor in here for that once we get the basics working. Um, but it's the maximum. Like it can't be longer than the shortest distance to the closest cell wall, or else you will overlap. And what we're gonna do is we're gonna make this, and then we just added these pre and post process methods, so we can go into our initialized node for whatever noise formula we want craters in. We can set the flag in initialize for pre-process to true, and or post-process, but probably pre-process. And then we can feed the position into that, and then we will do like a displacement ahead of time before we do our noise formula. And hopefully that will get us the best of both worlds. We can use our noise formula for things that it works well for. So like things where the precision works well and we're not getting like jaggies and precision issues. And we can use our pre-post process if we ever need anything custom. Taking a drink. Okay. So now that we've updated this should have no impact right now, I think, because they're already implemented. We shouldn't have to re-implement the virtual methods unless we want to. Let's make sure it builds, though. And I'm also going to eat some chips and salsa. Homemade salsa. Veggies from our garden. This salsa is really good. I make a banger salsa. So that's our plan for today. The adding the pre and post process like stuff to our interface should be pretty easy. This gives us a lot of potential flexibility too, which is kind of exciting. Things that we may not have been able to do because of our noise libraries limitations, we can now code ourselves. Not sure what just happened. We'll try it one more time. Maybe this. All right, if it crashes again, we know something's up. Okay. I think we're good. It might just be a one-off fluke. I haven't seen that bug in a long time, but we're just gonna call it a one-off unless it keeps happening. All right. Raider. All right. So I was chatting. Custom function. Structs. Functions. One. World radius. Give this a shot. I don't expect this to work. Yeah. All right. So obviously it needs more work. I wasn't expecting the first thing ChatGPT spat out to work anyway. Don't fall, please. Um, but for fine. Oh, derp. Make it unlit. Okay, that's what I thought. I don't think that's right. All right. We have our. Okay, hang on. We have this. So that didn't quite work. Maybe we should start from a working Voronoi implementation I made to do cell edge masking. We need to change the output from the X, Y, and Z from the I'm thinking here. Um, the output in each cell should return XYZ position of that cell's center. Here is the current implementation. We're just gonna give this a shot. We don't want to actually change it in. Um, all right, we're gonna clone this, except it's gonna be center. Now we can fuck with this without breaking our original implementation, which is actually quite awesome. Okay. Da, 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 da. That is looking closer. One thing is right still, because it's not following the actual cells. Like, we have these. We have these splits. Oh, but that might be. think it's correct. Each Voronoi cell should putting the same XYZ value for any point sampled, its bounds, and there are differences. Output cells XYZ color for any point sampled within its bounds should be the coordinate of the center of the cell. 3D space. Damn it. Fine. We'll just do it like this. Where did you get the frequency field from? That was not a field available for the original station. Not a lot of faith here. I might have to go back to Vader Toy. I think if we go back to Shader Toy, we can probably find something that's doing a little bit closer to what we need. I think the center points were actually being calculated in the one I originally adapted for this one. They just weren't being returned in the way that we want it. Hey, hey, hey. All right. All right. Okay. Maybe we are in good shape here. Okay. 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 Next, let's try this. All right. Flow v dist. V equals distance. V out. Scaled position. If v dist less than v out dot w, turn 1, else turn 0. All right, we got craters, sort of. This is great too because you get different scaled craters for each layer. You get a good variance and no overlaps, which is exactly what we want. So now all we should have to do is run the distance through a curve. Divided by right. Now, if we actually want the center of this, so I realized this would be an issue last night, right? So let's go to the drawing board. If if let's do it in paint. Say our center. So because we're working in three-dimensional space, our center could actually be above the surface of the circle. In which case, even here, we would have a distance, right? So what we actually need to do is project this center towards the center. We need to normalize it. We might be able to get away with just normalizing it. Okay, but that causes another problem, as you can see. and munching. I'm pretty sure we can just probably normalize a bunch of stuff in our Voronoi calculation. I got it. All right, not quite. Okay, so let's undo the normalizes. Undo this. Undo this. Okay, that works. Now, all right. First, let's just take it back here. I feel like if we're making these, then we should be able to figure out the center point. We're close. We gotta be. Ah, indist. And there it is. Ah, so we're going to need to normalize the calculations onto the surface of the sphere. I think it's becoming apparent. So instead of calculating the minimum distance to the wall from the center, direct center, we're going to need to project the center onto the sphere and then calculate the minimum distance to the walls that intersect the sphere. Works. Works, but I'm realizing something. We actually need to calculate the position of the center of the Voronoi normalized onto the sphere. And we also calculating the minimum distance to the nearest cell wall from the cell center. It needs to be from this normalized center. It needs to be the nearest distance to the cell wall's intersection with the sphere. We're also going to open up a new one of these over here so that we can always roll back because this is really close to what we need. All right, what are the odds this works? I mean, it's probably 50-50. It got the last one. clipping the edge. That only couple of cells with output, my understanding, think they should all output. Here is a picture of what I'm talking about. Let's redraw this real quick. Hey, Jinx. Jinx, God, do you have to do this in my face? It's pretty annoying, my man. Okay. Jinx, chill. Oh, God. Did you get your tail in my. Jinx. Gosh, you can be really annoying sometimes, cat. Stop it. Stop it. Stop it. Stop it. Oh, my God. Mm-mm. Quit. Tid center. Nearest. Leave me be. I'm trying to eat my fucking lunch. God damn, dude. You're being a little turd. Jesus, dude. No thanks, dude. I'm good. I don't do this to get subscribers. I do this so that I can keep an archive of the videos of me developing this project. I don't really care if people watch or not. Well, that's actually, there's two reasons I do this, right? I do it to keep an archive of videos of me working on the project and have them stored on somebody else's computer. A. B. I like to chat with people sometimes if they do show up, but I don't really give a shit if people watch or not. So I don't need like whatever product you're trying to sell. So this one here is what I did my distance map from. I can't believe this motherfucker just recolored the fucking shader the other guy put up. That's fucked. What a shitter. This one's kind of interesting. All right, we're just looking at options while I finish munching on my chips. All right, we're gonna go back to this for now. Oh, all right, I'm done with my lunch, which amounted to just basically the majority of a bag of tortilla chips and some fresh salsa. But now that I'm done with that, we can focus. Just putting the salsa up. Help Miss Violet back up on the couch. Violet, you need help? Violet, the gate is close to the stairs. You can't go that way. Come on. Come on, little girl. You got this. You can do it. Oh, good girl. You did good. You did real good. Okay. All right, so yeah, I think there may still be some confusion. The center position should not be the gradient center, but rather the actual center of the cell. In the case of the original distance gradient noise, for instance, would be the point in the cell, the lowest. The distance to the nearest distance from this center position to whatever the nearest point of its cell boundary are. Really, all these values would projections onto the sphere. So center of the cell projected onto the sphere, and then the walls only pay attention to the positions where the walls intersect with the sphere. Then figure out the closest, the distance from this projected position to the closest wall sphere intersection. Okay. Return V out. We'll just comment these out. Okay. So that's actually correct. thinking. Projected center, neighbors center, angular distance. Okay, so turn V out minus scaled position. Um, so I guess we may have a situation where a lot of the centers are actually outside of the bounds, but I really don't see the odds of that being very high with how big some of these nodes are. So when I run that, I only get one cell that has any points under distance to center under output W value, which seems wrong. Here is my code as it stands. I would have expected almost every node to have some points that would output from the if check where we compared their distance to W value. It may end up being easier to do this as like a triplanar. I'm gonna try one more time here. That's the same thing. That is the same thing. Maybe it would be easier to do this in a 2D implementation when our mapping. Let's try this. The Z output appears to be incorrect. It should be the minimum from the center point of the cell to its nearest cell wall. That means for any position sampled in the cell should have a constant value, but it is returning a gradient. Yeah, maybe try pointers the way. I mean, it definitely simplifies things because we can do all our calculations in 2D without having to project on the sphere. And then we can just lay them on the sphere with tri-pointer mapping once we have it working. Okay, again, that is returning different values within the same cell. The sample position should only have an impact on the cell that's calculated, but actual value should be a constant for each cell. So, for instance, if we have a cell whose center is at xy, the value would be the distance from that xy value, the nearest to the cell's closest cell wall to that center position. That means that if I sample multiple points inside the same cell, all of the output values should be the same for that cell because the distance is calculated from the cell center, which doesn't change, to the nearest wall, which also doesn't change. Okay, and let's come back up here. For an I2D, copy, paste. Notice in this screenshot, the returned Z value is still a distance gradient rather than a constant. I don't know what to tell you. It's obvious. Obviously wrong. Each cell's center to edge min distance should be constant value for all points sampled within the cell. Nope. Shouldn't we have to fully iterate the first two loops to find the center cell before we can find a constant cell distance? Okay. Okay. Alright, let's try this now. Vetus is this, and then we can do this. Teddy, it's the mailman. My God. 2. Um, Print screen. Okay, now I think we are returning the distance correctly. However, the position looks like it may be wrong. Once again, any sample within a cell should always turn the same XY value to the center of that cell. As you can see in the screenshot case. Let's give it a shot. Cell center. Be some variance here. Okay, this seems right. This does not. Nope, that has the same four quadrant. Last one again. Each cell, no matter where the point being sampled within it is, should only return a single XY value to the center of the cell for any point. All right, well, I guess let's look at it. Time to debug it ourselves. Hmm. Let's try this. Oh fuck. Hang on. Effect 2, replace with float 2, replace all. Effect 3, float 3, replace all. FP equals fract X. Get rid of this. So ND equals okay, let's start over with an implementation. Works. Here is a function saying edge distance. We want to change it. Turn the cell center in the XY and then is from the cell center closest edge BC. Also, it's going to have to be in 3D. So let's go back. Yeah, we're not going to be able to do because so we need the 3D function because we're not using it as a material. We're going to be using it as a C++ implementation. So it's no go on that. I'm just gonna go ahead and ban you, dude. No soliciting. Hmm. Okay, we are actually not going to be able to use the try planner because we need the function in C++ application. So going back to our implementation. Where's the fucking. Oh, God damn it. Note how the cell center output XYZ changes along the axis bound XYZ axis. This should not be the case since our sample point should still be inside the cell. The cell's center should not be changing on where XYZ sample takes place is the current 3D wave function. Hey, hey, this is what we were looking for now. Um, what about our distance function? Okay, this needs to return a float 4. All right, I think we might have it now. Maybe. Maybe. Let's try this. No, we do not actually have it yet. Without asking again. All right, I'm gonna be back in a minute. I gotta hit the restroom real quick. So I'm back. So I think we got consistent cell centers. Okay, I think we are now getting consistent cell centers that are not affected by this. However, I believe distance may not be what we need. Ideally, we would not be, if our min calculations are correct, our circles should not be able to overlap their projected boundaries on the sphere. However, this is not the case, and many of these are overlapping the current code. Not the case with the screenshot provided as a visualization. You can see the circles overlap this many cases. Center output affected. If our min distant, if our cell min center to edge we'll give it a shot. Actually, let's go ahead and copy paste this just so that we can keep it on hand. Hello. Okay, there we go. Go over here. Nope. Has the same issue. We need our distance value to be the minimum radius, the maximum radius of a circle starting at the normalized center that will not overlap any of the cell boundaries, which are intersecting units. Eddie, chill out. You spaz. You big old giant spaz. You're spastic. Nope, that code still has the same issue with graded circles often being the cell boundary off. Nope, that doesn't work. No, it's just the same. Let's take a look. Yeah, I know, right? Well, we're trying to here I drew some stuff. We're trying to do a custom Voronoi implementation with 3D Voronoi noise to do craters as a pre-processing step for a planet noise formula for like a rocky planet. So what we actually want to do is calculate the actual center of the Voronoi point wherever our sample point is and project that onto the sphere. But then we need the distance to the nearest intersection with the walls of the cell and the sphere, and I'm not sure how to do that. Um, because like, okay, let's take a look at the output here. So like, let's find one that's pretty obvious. So like right here, this one's actually pretty obvious. So what we basically want to do, so we have the centers calculating properly now, or the cell centers. So our cell center for this one, projected onto the sphere, is like about right here. Okay? And the next value we need is the minimum distance to the cell's boundary intersection with the sphere. And that should determine the maximum radius our sphere or our circle can be that we're going to draw here. Actually, just as an example, right? So that should determine the maximum size that our sphere can be. And we need this value. We need these two values. We need the center point, which we encode in the first three values of our float 4 output. And then we need the distance to the nearest wall at its intersection with the sphere. This is the part I'm stuck on right here. Um, but if I can get this, then you can see we can do a 0 to 1 distance field for that point, and then we can run that distance field through a curve and generate craters. And then what the and then we can fractalize it and do all that stuff. But like basically once we have this 0 to 1, we can just create a curve that looks something like this. So at our far edge, we're at this elevation. We go in a little bit, we're at this higher elevation, and then we like bottom out with like a little raise in the center of the crater, and that would generate like really nice looking crater height displacements. Fair enough, fair enough. But yeah, so that's what we're trying to figure out right now. We've already made it so that we return the projected hang on. We've already made it so that we return the projected node center points for each node. So like this encoded value is basically the XYZ value of this node's center point on the sphere for that given cell. The problem that I'm having is that I think the calculation is like fundamentally flawed because usually it works on the distance between 2 points, 2 nodes, and finding the minimum. But that doesn't really work because we're like intersecting with the original edges. So it's like I wonder if I could figure out how to normalize the original edges, maybe. But yeah, that's what I'm trying to puzzle out here. Once I get that, the rest of this is pretty easy. And I added to my noise generator, I added a use pre-process and use post-process flag because I had difficulties with Fast Noise 2 library occasionally. I'll show you what the problem is. So I made this in Fast Noise 2, this little crater generator, right? The problem here, though, is because I have to do so much manipulation of the Voronoi noise that I'm using to generate these craters to get them spread out like this, we lose a lot of precision. And when I get up close here, you can see that we're actually having like precision issues with the surface. So this won't work because these look fine until you spawn in your character and you realize that these are like 6 foot tall jagged spikes sticking out of the ground because of the scale of everything. So like these are small relative to the scale of the crater, but large relative to the scale of your character. So I need a function that will do this precisely without causing this type of effects. So I added flags to the noise generator for use pre-process and use post-process that will allow us to do our own offset calculations that are not using fast noise. And then we do our noise calculation here. And then we do our post process. And then we return the adjusted point. This allows us to either apply the displacement before we apply our noise formula or after we apply our noise formula or both. These default to false. So by default, you're not using either of these. But it gives me like a flexible way to add our own kind of custom displacement when we stumble upon a problem that we can't solve with like fast noise, the library itself. And so that's what we're working on right now. But to prototype it, it's actually easier to prototype it in HLSL because like whatever we do here would apply to what we're doing in C++. We would just have to create a C++ implementation of this. But converting this to C++ is a lot easier than actually figuring out the problem. And trying to figure this out in C++ would be incredibly painful because you'd have to recompile every time you wanted to test it, and it'd basically be impossible. So I'm getting the formula right in HLSL, and then once I have the formula right, I'm gonna look into like converting it into C++ and adding it to like a preprocess block for like our noise. So yeah, that's what I'm working on right now. And I'm just sitting here grinding my face on it. All right, what if I remove this? Let's go back to just let's get rid of these normalizes. The unnormalized, unprojected. Hmm. This is okay. Okay, this is wrong because it's taking the like um sample position coordinates into account, and you can tell because you can see these like perfectly square divisions where it's aligned with the axes. Uh, yes, set of mental block. Last time I used any geometry was for this code pen of dubious utilities. Yeah, I know, right? Like, I wouldn't worry about it too much. I'm not like a hugely popular streamer or anything. Um, Last time I used any geometry was for this code pen of dubious utility. Ah, yes, the rotating cube of doom. So something's going on here. Our this should not be taking into account our sample position at this point because all we should be taking into account is our projected center, neighbor cell, IJK, neighbor feature point. What is IP? Here you go, about it. All right. Um. It has to be IP. He's a float 3. So what if I do projected center? Ah! Okay, now it is not outputting a value influenced by the okay, so now we can test it. Oh, there's a dog on TV. Add our normalizes back in here, maybe? No. Nope, nope, nope. Fuck. Yeah, fair nice. That's actually a pretty good idea for a website. Just build a bunch of. I mean, like, you could do that. You could potentially do that with, like, Unreal and just use physics, but you could just model a bunch of different types of dice and then allow the user to roll any number of dice of any type. That's a cool idea. Um, so let's just take this, paste it over this. I had this, which is before trying to normalize it on the sphere or anything. I have this, which actually generates. Eddie, you can't handle it, huh, dude? Which actually generates our spheres a lot closer to what they should be. Let's try this. Atmosphere, bubble. I want a higher resolution mesh to test this on. There. So this is closer to what I'm looking for, but this is not normalized. So the problem with this is okay. Maybe I can draw it. So the problem with this is um, this is not normalized, so it's using the actual center and the actual minimum edge distance, which does a good job. God, Teddy, chill the hell out. Holy shit. He cannot handle dogs on the TV. Which does a good job of creating non-overlapping circles. So none of the it should be impossible for these to overlap. But the problem is, for example, right here, right? Our actual center point for this is somewhere out here. So when we do our distance calculations, we're not getting like a 1 to 0, right? We're getting like a 1 to zero point 0.5 or something like that, whatever the minimum distance is. I suppose, though, if we can calculate the distance of the difference of the distance of our center to the surface of the sphere, we could probably use that value to normalize this somehow. Okay. Hang on, hang on. That there might be something to that. So, because like this is actually perfect. It generates a bunch of varied sizes of craters that are not too close to each other, non-overlapping. Like I can visualize craters on the surface of a planet that look like this, right? So if we can just figure out how to normalize it properly, it might work. Teddy, you gotta chill. You gotta chill. Hey, I'm gonna punish. Hang on. No, no, Teddy, no, no, no. You gotta chill. Hey, no, no. Can you be good? Can you be good and watch TV like a good boy instead of making ruckus? Can you please be good? Come on, come on, come on, come on, come on. You and Trubs, you in big trouble. Okay, maybe he'll leave it now. Hopefully. Okay. So maybe I was approaching this wrong. Okay, good. It's going to a different episode. This episode had a lot to do with the dogs, so. So maybe I was approaching this wrong. If I use the non projected, non normalized algorithm, this output is close as seen in the screenshots, non overlapping, sparsely and randomly populated circles. Um, okay. So if that is the case, maybe instead, um, the main problem being that now our center points lie somewhere in 3D space, so we do not get a consistent 0 to 1 distance range when calculating our distance gradient. But perhaps we could calculate the difference in distance of the center point in 3D space to its projected position on the sphere and use this distance to somehow normalize our output distance gradient. Calculate the distance of the sphere. Use to normalize the gradient. Normalize the distance. Float 3 um C pause float 3 in pause VF dot Fornoy. No. We don't need that. VF dot XYZ. Normalize. v out dot xyz 3 d sphere equals distance c pause in pause. Oh, and then okay, um we are working on the unit sphere, so we don't need a radius. Okay, the distance to this, and then the min distance minus. Okay, I got it. I got it. I got it. I think. So, and then we have for v distance. Let's keep our Voronoi output as is and do this normalization step side. So the Voronoi output will be its actual cell center in the XYZ and its actual min distance to nearest cell boundary in W. We then want to take this output and figure out a way to generate circles way to we want to alter this part such that the distance gradient Let's try it. Aw, shit. Think we did it. Think we did it. Yep. Yay. All right. So this is the first part. Now we need to run this distance function through a curve. Okay, next up. Okay. Looks like that worked. Awesome. Now we have one more thing to do. We need to create a function that acts as a curve. We have a specific curve shape in mind. Okay, we have a specific curve shape in mind. I made a rough of it. X is a curve. It will take our distance value as an input generate a point, a y value, the curve as an output. We have curve shape in mind, a rough drawing of it. All right, let's give it a shot. Curve val equals bf dot custom curve indist curve val. All right, we got some donuts. We got some donuts. This proves that it can work. Let's make sure that we're normalized properly. Yes, we are. Okay, great. Okay, so this is a basic proof of concept of the idea. We need to figure out how to properly curve this because we don't want just a like what this looks like to me is the curve we're getting is like this, right? Something like that. Which is not what we want because it's not the shape of a crater, but it does prove that the idea is valid. So we just have to figure out how to make this curve with math. All right, so ha 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 ha. Let's go ahead and test some displacement here. Oh, it's a material function. Fuck. Ah, fuck. Okay. Well, we can go ahead. Okay, so here's our crater noise. We're gonna change this to center distance Voronoi. Multiply object radius times like let's do like 0.05 times vertex normal component mask XYZ. I'm getting a blister like on the side of my tongue that like rubs up against my teeth, and it's really fucking obnoxious and getting on my nerves. Our maximum displacement is going to have to be somewhat related to the scale of the crater itself. So like for example, these are smaller but they have the same vertical displacement as the larger ones. So like part of this is going to have to be altering this value at the very end based on how big it is. We can probably do something like divide the actual radius by the original radius or something like that. Um, Crater curve. We actually have the hardest part done now, I think, which is coming up with this. What if I just multiply? Yeah, we're just undoing it. We can figure it out later. Wait, I'm a fool. That actually appears to have worked. This is now higher than this, which is higher. Well, maybe works some. Oh, okay. What's up, dude? We're trying to. Okay. It's complicated, but I'm trying to. We have an issue with me trying to generate crater noise with the fast noise library because the operations I had to do on the noise to get craters like this um, are only using a tiny fraction of it, and we end up with precision issues up close to it, which you can see here. Um, so what I've done is I went into my noise generator and I added a pre and post process step and flags for that. Where when we construct our noise function, if we want craters, we should be able to flag one of these and then do our own noise adjustment before we apply our noise formula. Um, so that's part one. But then, in order to do this, we need a noise formula that can generate us some nice craters, right? So that's what we're working on here. We're doing it in HLSL first to get the formula correct, so that we have a formula that we like. And then once I have a formula that I like, I'll convert it into C++ and we can do it in the pre-process step. So basically, we did a custom Voronoi implementation um, right here that we're working on. I just got the distance working properly so that it generates like this kind of many different sizes and not like overlapping circles of distance radiuses. And we just added a basic curve function right here. But our curve function right now is just like proof of concepts. So like our curve function, I was drawing it earlier. This is the kind of curve function that we really want to generate like a crater. Right now our curve function looks more like this. This is not really what we want. So now we have to figure out how to make a curve function that'll generate a curve like this, which is like really, if we draw a sine wave, oh, I don't know if I'm going to be able to draw a sine wave by hand. If we draw a sine wave by hand shittily, um, very basics, we would want something like a snapshot of it, right? Yeah, so over the past couple of days, I've been making various noise formulas. So I have my basic like Earth-like planet, right? I have a lava planet formula, I have an ice planet formula, and I have a sand planet formula. The last formula I want to generate before I move on to the next step of the project, which I'm like kind of buttoning things up to put everything together in a like overarching planet generator, is like a rocky airless planet. Think the moon, right? Something with a lot of craters, things like that. And that's where I ran into this issue where I wasn't able to actually do that successfully with the noise formula I was using, because of the precision issues here. Because we could make this fractal and generate a bunch of craters, and from a distance, they would look okay. The problem is when you get up close to it, you have this like really nasty like precision issue, right? So like even it's even worse when you're it's even worse when you're at like surface level. You can really see that it's not good because while those look pretty small when we're just flying around over the surface, when we go down to the surface of the planet on foot, you're going to see what I'm talking about. Yeah, so like it's not great because these are like human-sized precision errors in the calculations of the noise. Wee wee, and it's kind of nasty. So we're making our own to do in a pre-process calculation, and that's what we're working on right now. It's this right here. So and the idea is that we would apply these as a displacement to the output node before we feed it into the noise. And so then all our noise layers can operate on top. Like think of it as shaping the actual crust of the planet based on its craters and then applying a noise function on top of that um, shaped crust to like add surface details, right? We also may add some like distortion, some slight distortion to this as well to make the shapes kind of not just absolutely perfect circles in every instance. Uh, but we pretty much got pretty far today. Like I got the goal of this distance mapping done, which is really important to what I'm trying to accomplish here. Once we get it all the way done, we'll have to do a FBM layer as well. Okay. Maybe we can do the curve externally, but we will still have to code it for C++. So, but for now, maybe we can just do it externally. We'll just return indist. Okay, we can go back here and change this to just return float in dist 0 float 4. Fuck, what the fuck? All right, so that's close. We're probably gonna have to make our own curve because these edges are not great. I guess we could do like a power here, maybe. Um, that might be a bit much. We could conceivably use something like this for volcanoes as well. Although I'm pretty happy with the volcano implementation and the noise function in the magma planet. Um, oh, easy. Easy, 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 easy. Okay. Curve. Um, haha, ha 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 ha. No problem. Something like this. I'll help you up. Hang on, hang on, hang on. Let me put the chair down. There you go. Okay, Violet, come on. You got this. Big jump. Oh, nope, not quite. Didn't quite get it. Oop, good girl. All right. How do I add a curve to this, though? There it is. And then... No, no power, no power. And also we're feeding... Okay, this. True. All right, we got craters. All right, let's clean up this function here. We have a lot of stuff that we don't actually need. All right. We're not calling either of these. Get rid of them. We're not calling this yet. Get rid of it. Leave the FBM. We're going to deal with that in a moment. Hey, little Violet. You want to chill and stop freaking out, girl? Voronoi is good. Smoothman is good. Hash is good. Okay, we're not using Smoothman. We can keep these. Am I using these? I don't think so. No. What are these? Or turn for V out XYZ in. Right, looks good. All right. Okay, we no longer need. We need this. We need this. We need this. We don't need these or this. The great thing about doing this procedurally as well is that we can do like ejecta, which should be fun. All right, so Voronoi FBM. Let's get the fractal shit going on here. The problem is like a lot of this logic is gonna have to go in here because oh, and the curve too. Because we can't just. Okay, hang on. So it's not quite correct, as it's not taking the frequency into account here. So we got to figure that out. So it's not properly counting for the frequency. So that's one problem. Fuck, there was something I had to do to fix this. Oop, that's not it. Hemisphere bubble. Excuse me. Oh, sudden hit. Okay. Bella, did you just poop somewhere? I smell poop. Alright, I gotta figure out where she pooped and clean it up. Hang on. Did you poop on the couch? You pooped under the couch. Okay. Alright, I see how it is. Oh, gosh. Let me make sure there's no poop on this couch.
Somehow you have pooped under a couch. You probably pooped on the couch, and I didn't notice, and then I let the chair down for you to jump up, maybe, or fall under the couch. I'm sorry about it. I just gotta make sure there's no poop under you. All right. So another thing I wanted to experiment with here, and we can actually do this pretty easily with this, is we could also do a volcano with this, I believe. So very interesting. But I am getting sleepy now, so I think this is a pretty good stopping point. We made a lot of progress here. I might just play some video games or some Magic for a bit. So yeah, later.